Okay, we're going to carry on today a bit like we did last time, in that still continuing to have a look at how to write algorithms. So this is just recapping from last time, just to get the point that when we're doing the sorting, remember that the outer loop there, that for loop, is saying start from the beginning, call the minimum position method, and it's going to find the smallest element sort of to the right in the array. And then swap is going to swap it into the first position. Then the for loop will move on to the next point. Minimum position will get the next smallest. Then we'll swap it into position number 2. And as the for loop progresses, we're carrying on. So we're doing minimum position swap until we get to the end of the array. So I just wanted to go over this again because I think last time a few people still were a little confused about what was going on. Are there any questions about this? Okay, one thing about programming style is that we could have put the whole thing in one big long method. So there's no reason why we couldn't have put all the code for minimum position and all the codes for swap in place there. But the reason that we've broken it down like that is for a few things. One is that by doing that, we're making it should be making it much more readable. That if you look at that code by itself, then knowing what each of the methods do, it should be possible to read that at a glance and pretty much understand the whole algorithm. Like when I say know what the methods do, all you need to know is minimum position will return the position of the minimum element. You don't have to know how it does it, right? And you can sort of drill into that later on to figure out what's going on. So one's readability. The other is that that also allows me to keep the high-level algorithm basically the same. And if I wanted to change the implementation either of minimum position or swap, I could do that without affecting the high level, right? Also, by breaking things down, you can reuse code. So those methods, minimum position and swap, might be useful in some other method or callable from some other method. So by identifying useful chunks of code and putting them into methods like that, you're usually saving yourself a fair bit of effort because chances are you come to write some code somewhere else and you think, oh, well, I've already got something that'll do a swap or find a minimum element, so I can reuse that. Okay? So it's pretty good programming style to try to decompose a more complex sort of algorithm into small pieces. It generally makes it easier for you to think about what's going on when you're designing it. And it also makes the code more reusable. And in a little bit, we're going to move on and look at another algorithm. And you'll see why breaking things down into methods is particularly useful in the way that we end up reusing it. Okay, so any questions about the sorting before we move on to the next bit? Yep.
Do we have to use this sort method, or can we source other ones?
There are lots of other ones.
Are we able to use like a standard method, like we use quick sort or something that we just pretty much copy and paste into our code?
Yes, if you had to use it for something, yeah. However, I hope you don't just sort of cut and paste without understanding what it's doing. So, besides that, a lot of these sorting algorithms are already in the Java libraries for a lot of these, or a lot of the data structures are there. Like say the hash map that you're using for the assignment, that already is a way of say looking things up in a collection, so you don't have to implement it again. Okay. So, if you remember, one of the reasons why we wanted to sort the array is that once an array is sorted, or once a collection is sorted, it makes it a lot easier to look up stuff. So if we had left the array completely unsorted, and we wanted to look up an element of the array, then pretty much the only choice we would have would be to go from beginning to end doing just an exhaustive search, right? So you could be lucky and find the element you're looking for right at the beginning of the array, in which case it'd be quick. If you're unlucky, it could be right at the end of the array, in which case you'd have to run through the entire array every time. Okay, so on average, it would take a half n, where n is the length of the array, to find this thing. And if you're doing that often, it's very slow. Okay? So now that we've sorted the array, we should be able to look things up more quickly. So here's an example. So this is the textbook, but let's pretend it's a phone book. If I'm trying to look up a name in the phone book, what's a fairly common way you would do it? So I'm looking up.
The last name.
What?
The last name. You say it's either a couple of.
Yeah, okay, I'm losing it. Yes, you're losing the last name, but if I want to find my name, so S, starts with S, how would I find it in the phone book? How would you find S, though? I mean, where do you know where it is like that? Right? Well, what you might do is open up the book, somewhere more or less in the middle, and, okay, I'm looking for a name starting with S. Now, here it might be, say, L. So I've opened up a page that's at the L's. So I can immediately discard the first half of the phone book because I know that S comes after L, right? Yes? Are we following this? So next thing I might do is pick another random page in the second half of the book, and it might be T, right? So now I know the S comes before T, so I can discard that, the last part of the book, and now I look in this one and do the same thing, right? So see what I'm doing? So what I'm doing, roughly, I'm cutting the array or the collection in half, comparing the element that I'm looking for with some of the elements in the middle of the array, and then discarding one part and looking at the other half. So what I'm doing is repeating exactly the same process, cutting the array down by halves every time until I sort of narrow in on where the entry I'm looking for should be, right? Now I say should be because there's no guarantee that the element you're looking for is in the array. But if it's there, then by successfully dividing it into halves, we narrow in very quickly, so much, much faster than a linear search. We narrow in very quickly on the element we're looking for, right? So that's called a binary search because we're binarizing, if you like, the array every time. And it's a pretty fast way of doing a search. So that's what we want to try to do now. We're going to carry on writing the methods in this class, but we're going to do this binary search. So this is just summarizing what I just said, that we've got our phone book, we pick roughly a midpoint, compare the element we're looking for, the key we're looking for, with the midpoint, and then depending on whether it comes before or after, we discard half of the array, focus on the other half, and do exactly the same thing over and over and over again. Right? Now, what's really important to realize here is that my binary search, if I start up with the entire array, and I split it in half, the procedure that I'm using is identical now on that half. Right? I'm doing exactly the same thing as I did for the whole big array on the half, and then the half of the half, and so on. Okay? So we'll see how that's going to be useful in the way we write it in a second. So anyway, let's just go through an example. So here we got an array, and it's already ordered for us. This is the array we used last time. And suppose we're looking for the item 12 in there, and we're going to use our binary search. So the first thing we do is find our midpoint. So the length of this array is 5, and we divide by 2 to find the midpoint, and 5 divided by 2 in integer arithmetic is 2. Right, so you remember this. So when we're using only integers in the division, the result is also an integer. So and what happens is that, like if this was a real number, you'd expect to have 2.5, but we truncate, and so we get 2, which is useful for us because that means that that if we use 2 as the index into the array, we get exactly the midpoint, right? So now we say, well, is 12 greater than or less than our midpoint 11? And it's greater than, right? So now we can discard this half of the array. We know it's greater than 11, so we take the midpoint plus 1. And now we repeat exactly the same procedure for this small array, which is just these last two elements. Now this is going to seem a bit weird because we're only down to two elements, but effectively it's the same thing. So, okay, so this is what I said, that now we're doing our binary search just on those last two. Now, we want to find the midpoint of these two elements. So that means that our starting position is the midpoint plus 1, and our end position is the end of the array. So to find the midpoint, it's the, well, can anybody explain to me that, how I'm doing that formula? What is the 3 plus 4 minus 3 on 2, where does that come from? Can you figure that out? Well, I'm trying to find, this is calculating the midpoint of this, the right-hand side of the array. Right, so remember, we're restricting ourselves to, we're pretending that all of that's gone, but we're still going to have an array that's numbered 0, 1, 2, 3, 4. All right? So the 4 minus 3 divided by 2 is, 4 is the position of the endpoint over there. 3 is the position at the beginning of the array. 3 divided by 2 should give you the midpoint of those, except that now they're all offset by the fact that we're starting from position number 3, right? So the 3 at the beginning is saying our array that we're considering starts from position 3, and then we add to that the midpoint 4 minus 3 divided by 2. Right? Does that make sense? And again, because it's all integer arithmetic, the 4 minus 3 is 1, so that's a half. Well, sorry, 1 over 2, 1 divided by 2 in integer arithmetic becomes 0. So then we're just left with the 3. Is that okay? All right, so the calculation of the midpoint is the offset into the beginning of the array and then the division of the, to find the midpoint. So in this case here, our midpoint turns out to be 12. And we ask, is the element we're looking for equal to the midpoint? And because we're looking for 12, we end up stopping. Right? So we found it. So next question is, if we do this search, yep, you'll find the first one, or whichever one in the order that your code decides whether it's going to look left or right, you'll find just one of them. This search is only to find if one exists, not all of them. Okay, but suppose none of them exist. Suppose you're looking for a different element. Suppose we're looking for 15. Now, in this case, we want our method to return the position of the element if it's found. So in the case of when we found 12, it's in position number 3, so we want our search method to return 3. If we're looking for something that isn't in the array, we'll get it to return something that clearly can't be an index into the array, so we'll get it to return -1. But the question is, how do we realize when we got to the point where it's not there? How do we know that the element we were looking for is not in the array? So we start. Sorry? Well, if they're the same, we're still okay. So we start out. Think of it this way: we're going to give the index of the start of the part of the array we're looking for and the endpoint. And when we divide it by 2, it's like saying, okay, we'll move that over here, and then we're looking in here. Then suppose it's to move somewhere else, we'll move that in here. We keep moving and moving and moving, squeezing the beginning and end points of the search. If we find the element, this beginning and end should coincide, and we find the element at that point. You'll see when we look at the actual code that if it's not there, they'll end up passing each other. Right? At that point, you know that you won't find the element. All right? So you need to know this in the way that we're going to end up writing the code. Okay, so here is the code for the binary search. And there are parts in there that look a little bit like magic. Because, well, what's looks funny about that code? The method is called search, and it calls methods inside it. What methods does it call? So it's calling itself. Right, this is a method that calls itself. That's called a recursive function. So how could that possibly work? Well, remember we said that when you're doing the binary search, when you chop your array in half, the binary search is exactly the same. The method itself is exactly the same on that half of the array as it was on the full array. So the parameters that we've got there are we pass the array that we're trying to search, v is the value we're looking for, and to and from the index is telling us the beginning and end of the range of the search inside the array. Right? So that's saying look inside the array A for the value v, and you can start from position from in the array and end in position 2 in the array. Okay? Now, have a look at the parameters of these calls to itself and tell me what's going on there. I know it's tough to stay awake this late in the afternoon, but give it a try.
The first one, the mid minus 1 becomes the end, and 2.
All right, so we're going to execute this one if the thing we're looking for is less than the midpoint, right? Because this is saying search inside A for v, starting from, which is the same as got passed in the first place. But now we're going to limit our search to the midpoint minus 1. Right? We don't have to look at midpoint because we've already looked at that. So that's saying look in the first half of the array. This second one is saying if the element we're looking for is bigger than the midpoint, then look in the second half of the array. Right, so does that make sense? Now, the thing I was saying about sort of magic about a recursive function is that when you're writing it, you kind of have to believe it's already written. Right, it already works. And if you do, if you keep that in mind, you say, well, since it already works, I can call it again. Right, so since I have to do a binary search, I'm writing a binary search, but since I have to do a binary search on the half of the array, then it'll call itself. Right? And as long as you do all the right things, that will work. So there are a few important things about this that are in the if statements. So first of all, let's see what the first if statement. If from is greater than 2, return minus 1. What's that telling us? Right, so remember what we're saying, that if the value isn't there, we'll keep shrinking from and to, sort of, so we'll start out and we'll go bang, 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 bang. So eventually, if we can't find the element, these things will surpass each other. So the first one is saying, if it's not in the array, then return -1, which is our signal for saying this is a nonsense index, so it's not there. The next bit is calculating our midpoint, the same as we did before. So from is saying, okay, we're offset into the array up to this point, divide by 2 to work out the middle of that, and that's our midpoint. The next part, so let's go through this, the next part of your statement. If the value we're looking for equals the midpoint, or the value in the midpoint, I mean, then what are we returning? I've got to wake people up. Can you tell me? Sorry? Okay, so the mid is the index of the midpoint, and that represents the position of the value we're looking for. So it's like we've succeeded. The next bit is saying that if the value we're looking for is less than the value in the midpoint, look in the sort of left half of the array. And the only alternative left when we go down to the else is that we look at in the right half. Okay, so does this make sense? No problems with that? All right, so the important thing about a recursive program is that you must have these two elements in there. If you have, so in the second part we say one or more recursive calls. So in the case of the binary search, we've got two recursive calls. It can call itself either to search the lower half or the upper half of the array. That's okay, but if you don't have a way of terminating this recursion, then what will happen? It'll keep calling itself forever, and eventually you'll get an error called stack overflow, which means that you've run out of memory because so every time it calls itself, every time a function calls another function, the system has to keep track of that call and know where to come back to when you continue, right? So all of this is pushed onto a stack. It's like a stack is a list where something that goes in first also comes out first. So it's like stacking things one on top of the other, and then you unstack to look to take stuff off. So if you have a recursive function and you're not careful about the termination condition, this will just keep recursing forever, or not forever, but eventually you run out of memory. So the two elements you must have are, first thing is check when does it terminate, and the second part is the recursive thing. So in our thing here, in our code here, the first two conditions in there, one is terminate if you can't find the element, the other one is terminate if you have found it, and the other two are the recursive bits that say keep looking, right? So a recursive function is pretty much always structured like that. It'll have an if statement that has, or at least some if statements that'll have a check for termination, and then something else that'll say if you're not terminating, here's the recursive part. Right? All right, so let's see if we can run. All right. So there's our code. It's actually the same in in Java. Now this is the main method that we had on Tuesday, and the only thing that I've done is I've added in here to do a test a sorted array, and here I'm calling search. So we're saying search on array B, which is this thing. I'm looking for the value 20 in this array. And initially, when we call it, we're going to call it on the entire array, which means indexed from 0 to length -1. Okay, so that's the initial call to the search routine. And if I can find the right main method. We'll call this. And just by luck, no, hang on, what's going on here? I may have picked the wrong file here. Oh yeah, that's right. Let me put in something else first. All right, just by luck, if we're looking for 20, oh no, it's not by luck, this is what I meant. 20 is in position number 3, right? So it executed, found the right value, produced the thing that we wanted. Now let's say we try looking for something that we know isn't there. Okay, now we get a -1 produced. So now I was looking for 95, which is an element that is not in the list, in the array. And this time around it gives me the -1, which is what we wanted. Right, okay. Now suppose you're writing this function, or the method. What sort of things will you try to test that this is all correct? So apart from reading your code and trying to convince yourself that logically it's working, what you always need to do is devise a bunch of different tests that will really test you work out whether your code is really doing the right thing. So did Malcolm mention this in his last lecture? Yeah. Talk about testing? So what sort of things did he say that you should try to do? Can you remember? No? Wake up. Can you remember? No, you're asleep too. Yeah, but apart from sort of the mechanics of it, which we'll probably go into a little later, just what sort of principles are that you should always try out with the testing? Like if I've now tested that it can find one element that I know is there. I've now tested that it will realize that if there's an element that I'm looking for that isn't there, it'll give you the right answer. So that's 2 tests that I needed to do. What other sort of variations could you think of that are worth trying? Yeah.
Can you give it a really, really, really big number?
What would be the point of that? You've got to be useful tests. Well, so if we're checking the boundary conditions, what would you do? What would you test? Sorry? You could try making from and to the same, okay. What else? Sorry? Yeah, I would try to see if you can find things that are right at the very beginning or right at the very end. What else? Yeah, true, but like we've already said that this algorithm will only find one of them, but as long as it finds one, yep. So this one here, I think there is a case where, yeah, so here there are 2 62s in there, right? It'll find one of them, but you don't, right, in our case, we don't care which one. So if we look for, change this to look for 62, it finds, I'm not sure actually which one that is, but it'll only find one of them. That's okay, this algorithm wasn't designed to find more than one. Yeah, you'd have to count, I'm not going to do that. What else would you test? So that array is of even length. I would test it if it worked on an array of odd length. Right? So anyway, so when you're working through, it's usually these sort of extreme or boundary conditions or variations like odd, even, stuff like that, that you need to be testing. Because once you've got the basic logic of the algorithm right, the most likely thing that will go wrong is minor things. Like, I think when I was doing it, I wasn't thinking very carefully at first, and I did something like mid instead of mid minus 1 or mid plus 1. So you can make mistakes with, am I at 1 over or 1 under? Or have I divided by half instead of something else? So to test, usually those things come out if you test all these boundary conditions. Okay? And it's really important. So when you're writing your code, you're not just writing the code, you also need to be thinking, how do I test this? And the best way of doing this also, and BlueJ helps you with this, is that when you write a function, test the function by itself if you can. Right? And with BlueJ, like I said, it's easy to call a function all by itself and test it returns or does the right thing. If you try to write all your code out in one go, edit it, put it all in, it compiles and you say, oh good, it works. A program that compiles and it hasn't been tested is not a working program. If you come to me and say your program works, I will immediately ask you, have you tested it on a range of different things? And if you say no, I will say, you're lying to me. It's not a working program. Right? So it's only working if it's been thoroughly tested. And the way to do it is to test it in pieces, because if you try to test a program that has a lot of methods in it, already written, or classes and methods, and something goes wrong, then you've got to try to backtrack and figure out, well, where is the error? And if you've got one method calling another method calling a class over here and a class over there, and things start to give you strange output, then how are you going to track down what's going wrong? All right, so you've got to sort of chain back through all the connections between classes and methods. So the best thing to do is, as you write a method like that, you test it by itself, assure yourself that it's doing the right thing, and then when you put everything together, you'll at least have confidence in the pieces. So when something goes wrong, it's likely to be somewhere else. Okay. Now we're going to move on to something else. Related. Where are we? The sorting and searching that we've done has been on primitive arrays of integers. But if I'm doing this for real, or in a more realistic setting, then my collection of objects is not likely to be a simple thing like numbers. I mean, sorting an array of numbers doesn't get you very far. What I'm more likely to do is something like the example that we had of implementing a phone book or a database where you've got to search for complex objects, like there could be your accounts. Right, so the hash map that you're using in the assignment is using a different method for searching a collection. It's called hashing, which we won't go into, but it's a very fast way of doing a search, even faster than a binary search. But what you want to do there is not store just numbers, you're storing accounts and transactions and stuff like that. Or if in the case of the phone book, it's an object that has at least a name and a phone number and probably other things like addresses and stuff. So now the question is, if we want to do this kind of sorting and searching, I don't want to have just an array of numbers. I want to be able to do this on an array of objects. And for our purposes, let's say it's going to be a phone book, and the objects that will be contained in these arrays, the phone book entry will just be a name, which is a string, and the telephone number, which we'll also treat as a string. We don't really care if it's a number, right? So the job is to adapt the sorting and searching methods that we've already done, but have them applicable to an array of phone book entries rather than just numbers. So I've already written our phone book class. Where are we? So we'll just call it an entry. And the entry consists of two fields, which is the key value. So when we talk about a key, that's usually the field that we're going to use to do the lookup. So when you're looking up a phone book, it's usually a person's name. So in this case, the key will be a person's name. And the value that we're looking for in this case is going to be a telephone number. But we almost always have at least a pair, like a key value and key and a value. All right, so we've got our usual stuff. This class is very simple. We just got our usual stuff of a constructor that will create an entry object that has the key and the value. We've got our two accessor methods that will give us access to the private fields. Okay, so the most important thing that the entry class has to implement is a way of doing a comparison. When we are doing our searching for the numbers into the integer array, then it's really easy because we're just saying x less than y. It's just a numerical comparison. That's easy. But remember, in the tutorial from a week or two ago, the cards one, remember that you had to do some comparisons of cards. Well, when you tried to find the smallest card, how did you compare cards? Remember, the card consists of a number and a suit. Remember that? Yes? Put up your hand if you remember having done that. How do people not remember what they did in the tutorial? So the card consists of a number and a suit. So it's two components, and it's an object. So how does Java know, if I want to compare the ace of spades with the two of diamonds, how does Java know, because these are objects that you've created, how does Java know which one's smaller than the other? So how? What did you do, the people who have done it? You guys. What did you do to compare cards? If you have the cards you had in the tutorial from the week before, whatever it was, if I want to say this card is less than that card, how do you compare them?
So does that mean so you look at the suit first and then the number? I mean, so you look at the number first and then the suit.
Yeah, okay, so the thing, well, yeah, what's the normal way of actually comparing cards in a... Do you do the suit first or the number first? I can't remember. Number then suit, okay. But the point is that comparison, because you've created the object yourself, you can't use the less than operator that's built into Java because that only applies to the primitive objects that Java knows about. If you want to compare objects that you've created, you have to tell Java through a method how that's to be done. Now, so an example of that is the string class, which is built into Java, has a compare to method that allows you to do an alphabetic comparison of two strings. So you can tell that like ABC should come before DEF, right? So there's a compare to method built into the Java library, for the string library, that tells you how to do a comparison. So I think you did have a look at that with Malcolm, didn't you? Or at least the equals or something like that. He told me you did. So this is another one that sort of went in through one ear and out the other. All right. Anyway, so when you define your own class and you want to do comparisons, you have to do your own, tell basically Java how to do it. So we're going to write in this entry class a compare to method. And so key, what type is key? It's a string. So I just said that string has a built-in compare to method of its own that'll compare strings. So here is a string, so key is a string, dot compare to, and if x is another entry, so we're trying to compare two entries, two phone book entries. And a phone book entry, the ordering will be just ordering on the key value. Right? We're not going to, so if you're looking up a name in a phone book, you only care about the person's name, not you're not ordering on the phone number. Right? So if I want to compare two entries in the phone book, I just get the key value, the name of the person, and compare that. So here is my entry, and I compare the key value of the current entry, and if I want to say is x, compare x with this entry, then I get the key value, which is another string, and compare it to the key value of this entry. Right? Does that make sense? Now, okay, I might confuse you next. Has Malcolm talked about overloading on methods? Okay, so we've now got two methods called compare to. What's the difference between them? All right, the type of the parameter. So Java allows you to use the same name for a method if it has different types for its parameters. So there are two cases you might want to do. You might want to compare an entire phone book entry with another phone book entry. Or in our case, because what we want to do is look up a phone book entry given a name, and a name is just a string, right? So there are some circumstances in which I might want to compare an entire object with another object, in this case an entry with an entry, which is what the first version of that method does. The second version says, I just want to compare the key value of the current entry with a string that I give it. So we're going to use that next, because when we do our searching, we're just going to give a name for the person and look for the entry with the right value. Okay? So overloading, so it means that you can have a method that has like two different signatures. So remember what signature means, the method plus all the types, the return type and the types of all the parameters. So this is, when you have two different signatures, that's called overloading on the same method name. So compare to, for a string, returns an integer value. If the two values you're comparing are equal, then the value it returns is 0. If one is less than the other, it returns -1 or some negative number. If it's greater than, it will return a positive number. Right, get that? So if I do a comparison, if I do x compared to y, and if x comes before y in our ordering, we'll return -1. If x and y are the same, I'll get 0. If x comes after y in our ordering, I'll get plus 1, or at least a negative number or a positive number. Right? So we'll use that in a bit. How's our time going? Okay. So this is what our main method is going to look like. So what I've done here is I've made a copy of the class, the sort and search class that we just looked at for the sorting and for the binary search. So I just copied it. I've changed the main method there so that we're going to test it with, so we're going to create a really short array. So A is an array of entries, and I'm just putting 3 entries in there for now, because I didn't want to write out a whole big long array. But I'm going to do exactly the same as I did for the integer array. I'm going to print it out, I'm going to sort it, print out the sorted version, and I also want to do a search. This time our search is going to be, I provide a string, which is a name of the person I'm looking for in the phone book. And what I want it to be able to do is find the corresponding entry. All right? Now, what we are going to do together is, well, probably not now, but next time. That's the original code for the integer, working on integer arrays. What we want to do is work our way through that code and fix it so that it'll work for sorting and searching arrays of entries, not just arrays of integers. Okay? And I'm not going to do this. I want you to tell me how we're going to do it. So what do I have to change to? So this is the print method, remember? This will go through an integer array, and it'll print all the elements in the array. So what do I have to change in that method to make it work for an array of entries? And the hint is it's really, really simple. I have an integer array, I have an entry array. What? Into a string? No, it's an array of entries, right? So that's the only thing I have to do to make that work. Going back to this one. Do you remember what toString does? And I'm sure Malcolm has told you about this. Yeah, and a little bit more than that. So, okay, so this is a method that will take our key value for the entry and the value, and it'll concatenate them together to form a string which is like key, colon, space, value. But what's special about the toString method? By convention, when you say print an object, Java will look to see if you've defined a toString method for the class of the object, and it'll use this to convert your object into a string, and it'll print that out. Right? So if you just say print entry, Java will know, because we've written this toString method, Java will know to use that to format the print the way that you've told it. Okay? So that's why over here we didn't have to change anything other than the type of the parameter, because when we do the print, so when we call system.out.print or print, the A of I, the type of A of I is what? Like the ith element of the array is what? Type 1? Entry. Right? So A of I is entry type. And because we've told Java using the toString method how to convert an entry into a string, Java picks up, actually executes your method, gets that string and puts it in there to print out. So that's nice because here that we haven't had to do anything other than change our parameter from int to entry, and it all still works. So we had to do minimum work to do the conversion. Okay. All right. So we're out of time. We'll carry on next. Well, next week's the break, and the week after, and hopefully when you're Tuesday morning, you'll be a little bit more awake.